Okay, so welcome to the dot product. We're going to go over some of the how you do the dot product and then some of the functions in this video. So let's start off. Let's say you have two vectors, A and B, and you take the dot product. To do that, you just write a dot between them, and that indicates that we're going to take the dot product of A with B. So let's say A was the vector 0, 1, and B was the vector 4, 5. The way that you take the dot product is you multiply component-wise, and then you add. So you would have 0 times 4 plus 1 times 5. And so that just equals 0 plus 5, which is 5. And so that's the dot product of A and B if A was 0 and B was 4, 5. 0, 1 and B was 4, 5. So we could do the same thing with 4 dimensions. So let's say A dot B is 1, 2, 3, 4. And B is 0, -1, 4, 3. So we do the same thing, and it works in as many dimensions as we want. We have 1 times 0 plus 2 times -1 plus 3 times 4 plus 4 times 3. So that just equals 0 plus -2 plus 12 plus 12, which is just 24 minus 2, which is 22. So in this case, we can take the dot product of vectors at whatever scale that we want. And so by this definition of the dot product, by multiplying component-wise and then adding, we have some insight into the magnitude of vectors. So note that the magnitude of A, as we defined earlier in a different video, is just A1 squared plus A2 squared plus A3 squared and so on, right? Because keeping in mind, A is just the components A1, A2, AN, right? So with this as the definition of the magnitude of A, we can write this out a little bit differently and expand it. So we have A1 times A1 plus A2 times A2 and so on. But realize that how we just defined the dot product, this is actually just the dot product of A with itself inside of here. So this is really just a square root of A dot A. So these are actually equivalent functions, equivalent measures. And the other thing we should realize about the dot product is that if we have two vectors, say A and B, again, and they're orthogonal to each other, so let's say A is here and B is here, so that if we put them next to each other, there would be a 90-degree angle in the Euclidean plane, so that this is pi over 2, then the dot product of A with B is 0. So let's do that numerically for a second. So say A is -1, 1, and B is 1, 1. So that looks pretty accurate to what's going on here. And if we take the dot product of both of these, we end up with -1 times 1, which is -1, plus 1 times 1, which is 1, which sure enough is 0. So we just confirmed that if we have two orthogonal vectors, the dot product of both of those vectors is 0. And that's actually important for defining the cross product and some other features of vectors that we'll go into in other videos and in other JOLTs. Now, from this definition of a dot product, we can find some interesting ideas about triangles. So recall the law of cosines for a triangle. So say we have triangle A, B, and C. So from this triangle, realize that C is just A minus B. Because if we have A here, and then we add -b to it, we get C. So sure enough, this is true. And we'll now look at this triangle from the law of cosines that we defined, in middle school, and this law that we know pretty well. So the law of cosines is just C squared, so this length squared, equals A squared, this length squared, plus B squared, minus 2 times A, B, cosine of theta, where theta is this angle. And we're not dealing with anything orthogonal right now. That can be any angle between 0 and pi over 2, really. So because, now let's use this fact that we just found out, that C is A minus B. So if we plug this into here, we can get this same equation. And multiply on the right side. And so by multiplying A minus B squared out, we end up with A squared minus 2A dot B plus B squared. And realize that this A dot B arises because this is all component-wise multiplication. So A squared is really just A dot A because we're taking all the components and multiplying by each other. So we have this on the left side of the equation equals A squared plus B squared minus 2AB cosine of theta. And as we normally do, we can simplify this by canceling out the A squareds, canceling out the B squareds, and we can in fact divide both sides by -2. We'll do this all in one step just to keep it simple. And then we have A dot B equals AB cosine of theta. And recall, these A's, as we defined in this equation, is just the length of A. So really this is just the magnitude of A, the magnitude of B, cosine of theta. And this is our key result from looking at this law of cosines. We took this formula for just a triangle with vectors, and we took the law of cosines, put them together, and we ended up with this cool equation. And so we're going to just see right now what we can do with this equation. What does this tell us about vectors and what we can learn from the dot product? So we have, I'll just rewrite it, A dot B equals A, the magnitude of A, times the magnitude of B times cosine of theta, which is the angle in between A and B when their tails are put together. So what can we learn from this? Well, we can solve for any of these pieces if we have all the other ones. So if we have A and B, say in component form, let's say we just have an arbitrary A and an arbitrary B, well, let's say we want to know this angle theta between them. What is that? And let's say we don't know the angle, we don't have a protractor, we can't directly measure this. Well, we can solve for theta using this equation, and the dot product is going to come to our rescue to do that. So if we solve for theta, we can just divide both sides by the magnitude of A times the magnitude of B, and that's going to give us A dot B over the magnitude of A times the magnitude of B equals cosine of theta. And so taking the arc cosine of both sides will give us the cosine whose angle is A dot B, magnitude of A times the magnitude of B equals theta. And there we go. We solved for it. So we could actually do that with this. Let's say that this component, let's say A really equaled -1, 2, and B is 2, 0. Then we can solve for this angle theta between them. These are pretty accurate. Maybe this is 1 and that's 2 and that's 2, and it doesn't go up at all. So by plugging this in, so now we have theta equals the cosine whose angle is A dot B, which is -1, 2 dot 2, 0 over the magnitude of A times the magnitude of B. So the magnitudes of both of these is, so the magnitude of A is 1 squared plus 2 squared, and then you take the square root. So that's a square root of 5. So the magnitude of A equals the square root of 5. And the magnitude of B is 2 squared plus 0 squared, the square root. So the magnitude of B equals 2. And so we can plug all this into the equation, and that will give us, and then we take this dot product. So the dot product is going to be -1 times 2 plus 2 times 0, which is -2. So we end up with the cosine, arc cosine of -2 over 2 times square root of 5, which is going to equal the angle whose cosine is -1 over root 5. Now, I'm not a calculator, and we'd have to go to our tables for this, but that is going to give us theta is this value right here, which can easily be calculated with tables that are well known. And the last thing we can do with this equation that's pretty interesting that we're going to go over right now is rearrange this to find the formula for projection, which pops up in physics and mechanics all the time. So if we divide both sides of this equation by one of these magnitudes, let's say the magnitude of b, then we find that a dot b over the magnitude of b equals, those cancel, the b's cancel on the right side, magnitude of a times cosine of theta. Now, if you take in physics or you remember your formulas a little bit, you'll realize that this right here, the magnitude of a times cosine of theta, is actually just the formula for the projection of a onto b. So if you don't recall what that means, let's say we have a and b. The projection of a onto b, you take a perpendicular line from the tip of a down to b. It's just this length right here. So the projection is just a length of the projection of a onto b. So, for example, if you were pulling a block, let's say these were forces on a block, and you were pulling it, and you're pulling it up a little bit. So you're pulling it not only horizontal to where it's going, but because it's such a heavy block, you can't actually pull it directly. You're only sliding it across the ground. By taking the dot product of A with B, this value that it gives you is the horizontal force that you're actually putting into the block that will cause it to slide along this direction that you're pushing it. So that comes up in all sorts of different physical properties in mechanics. And with that, we really have covered the dot product. We went over what it is, how to calculate it, the formula for the angle between two vectors using the dot product, and now the formula for projection of two vectors, one vector onto the other. And the dot product has come to our rescue in all of these and is a crucial tool for solving equations with vectors.